know whether people replied. Maybe you can. Yeah, you are recording.
Yes,
Right.
I just started.
Okay.
Okay, so guys, thank you for joining us. We've got a very special talk, as you've just heard. Christos has, well, I'll let him tell you himself, but he has a very full CV, a lot of experience, and his team as well, I know, are very experienced. They're working on some really groundbreaking stuff in robotics and surgical intervention. So I'll let Christos talk a bit more in a second. Just a bit of housekeeping. So Christos is going to give us a little introduction, and then Carlo and Claudio will present to us. If you have any questions, you can either drop them in the chat if you don't want to read them out yourself, or at the end, you can raise your hand and ask them yourselves. That's all right with everyone. So, Christos, if you're ready.
Yeah, so basically, yeah. Thank you very much for this introduction. I mean, I'm basically I'm measured by the success of the team. So it's one thing in academia that we should all keep in mind, that the PI tends to get a lot of the glory, but really the work is done by the team to the maximum extent. So I want to thank Carlo and Claudio and everybody else for. Well, actually, making everything happen. I'm there to. I'm a glorified administrator to a certain extent. Yeah. So anyway, that said, okay, I do have some input, but anyway, thanks a lot. So these guys are really contributing to the two pieces of research that they will present. Carlo is instrumental in anything that has to do with making the robotic systems in our lab. He's fairly senior, so he's also managing the new facilities that are being designed for surgery and intervention at King's College London. And Claudio is now a fourth year research assistant with the team. Yeah, so he just finished his third year. He's doing his PhD with the team. And he's working a lot on interventional image analysis. So really you have the two of the core people that make the robots happen on one side and make the robots do something on the other side. So really, I hope this combination is giving you a good overview of what we're trying to do. Now, a little bit on the team, we are around 15 people, various levels, entry-level PhD students, more senior people, postdoctoral researchers, and we are also supervising a few undergraduate researchers as well. So some of you also are working with us in various projects. So. And really, the team has two branches. The one is the mechanical engineering aspect, and the other is the interventional image analysis. And really trying to bring the two together to do some sort of autonomous robotic systems is what we are aiming for. And finally, we are part of the School of Biomedical Engineering and Imaging Sciences and the Department of Surgical and Interventional Engineering, which really aims at bringing this, new technologies to the clinic. So I think I spoke enough. So I don't know whether you, Claudio and Carlo, have decided of a specific order, but maybe Claudio, you can start with some of the images that we are looking at for the team, and then Carlo will continue with discussing the latest and greatest in the robots that have been developed in the team. All right. So I'm gonna mute myself now. Claudio, on to you.
I will share my screen. Can you see my screen?
Yes.
Yes, okay, perfect. All right, yeah, so I'll be talking about a paper that we published earlier this year. Us being mostly the kind of image processing, computer vision side of the lab, called Learned Optical Flow for Intraoperative Tracking fundus, which is a bit of a mouthful, but I'll try to explain what's going on. And this is kind of what I've been working on for 2 years before that, and what I'm trying to develop further currently. So the background of the whole thing. So here we're talking about vitreoretinal surgery. So this is minimally invasive or keyhole surgery inside of the eye. So on the left you can see an eye kind of in a close-up. For the surgical setup, so in the surgical setup. And so what happens there is that essentially holes are made in the sclera, that's the white bit in the side of the eye, through which the so-called trocars are inserted. So those are kind of little sleeves through which then tools can be inserted into the eye. And the surgeon can then see the tools looking through a microscope, which in itself looks through the eye's lens towards the back of the eye where the retina is. The thing that's ideal there is that generally the part of the retina that the surgeon is interested in is right opposite the lens anyway, because that's the part that really mostly looks out. So we can also basically look the other way, look in and see the retina. And then on the right-hand side here, we see a few of the tools that are being used. So for example, these kind of really small forceps and a cutter and a light pipe. I mean, the edge on the cutter is so small here that you can't really see it very well. The light pipe itself is essentially just a light that shines into the eye so the surgeon can see something inside. And the shaft of those tools is maybe what, 1.5 millimeters diameter, something like that, just so you get an idea of the size of this in real life. So now, currently, there's a number of new procedures that are being developed, for example, to do with genes, stem cells, but all of those require a higher precision than what surgeons can currently deliver manually, because the entire operation is still done manually, so that the surgeon operates these tools that are inserted into the eye by hand and has to move them extremely carefully, millimeter by millimeter, just trying to get them to move to the right location. And you got to think that essentially the insertion point works as a fulcrum, kind of as a fulcrum point around which the tools are rotated, so you can't just move them sideways, because otherwise you'd be tearing the holes in the outside wall of the eye, essentially. So you can't do that. So it's very, very difficult and careful operation there. And just due to natural things like hand tremor, which you always have, even if you're the best surgeon, you've got really steady hand. At some microscopic level, your hands are always shaking a little bit, even just due to heartbeat. And that just limits the precision that you could possibly deliver. And some of those newer procedures need higher precision than even that, because you need to get to a very, very specific depth in the retina, a very specific layer, specific type of cells, things like that. And so computer vision based knowledge of retinal motions, so that you can track surgical targets, i.e. track points on the retina that you're interested in for a surgery, that is useful both to current surgeons and also for novel robotic tools, which I think Carlo may be talking about more later, which are being developed to kind of tackle the problem of precision. And this whole thing is quite challenging because the intraoperative images, so the images taken during operations, are not always as nice as you'd want them to be. So here you can see two examples. These are videos taken during actual surgeries. So you can see the round field of view of the microscope that is looking through the eye's lens to the back, and you can see the retina back there. You can see the tool. You can see that there's the light pipe to the left. The tool casts a shadow on the retina. The whole thing is kind of moving around. There's a lot of blurring and motion and so on and so forth. So it's a relatively challenging thing to track a point on the retina robustly. And so here, for example, we have a number of things that happen. So you have shadows that are cast on the retina. Sometimes the tool shafts are not very clearly visible against the retina due to the illumination, and also because they're metal and they essentially reflect some of the surrounding retina. Then you can have things like glare on tools that can throw off normal tracking methods. You can have blurriness, shape distortion. You can have a partially occluded field of view, so your field of view through the microscope isn't always a nice, perfect round shape. Sometimes it's kind of partially occluded, as you can see in the left lower corner. Uneven or dim lighting, because you really only have that light pipe that goes into the eye and illuminates the retina. And as that moves around, the whole thing can get brighter or less bright. That just also makes tracking more difficult. Then sometimes the lens of the microscope itself is visible. As you can see here, this kind of round shape, mostly visible on the left-hand side. There can be particles or droplets sometimes on the lens itself, which partially obstructs the view. And finally, also, if you zoom in enough, you can also just see compression artifacts on the images themselves as they are currently captured from the microscope. So our overall approach, right? We want to be able to track specific points on the retina despite all of these things that I've just shown on the previous slide. And so our overall approach for that is to use optical flow, because that allows us to get dense motion estimation, which means that we get a motion vector for each pixel. So from in a video, from one frame to the next, we aim to be able to tell where each pixel went, which gives us the maximum amount of information about the overall motion that is present in the video. And for that we use deep learning, because that gives us, these days, that gives you better quality and also fast inference, meaning that you can actually use it in a real-time environment. Eventually, when you deploy it in an actual operating theater, it'll be able to run in real time. And we also combine that with a segmentation output. So basically, we try to predict the motion of objects, and we also try to identify the objects themselves that are visible. Mostly just which part is actually retina and which part are the surrounding kind of dark areas outside of the main field of view of the microscope. So the problem here is that if you do use deep learning in general, you need a lot of data to train the models. And a lot of data itself, that's not a problem. We have a large data set. We have a lot of these videos. We've got lots of images. The problem is that this data also needs to be annotated. So the training data needs to have the input data and then kind of sample output data so the network can be trained with what would be the correct solution, right? So you need to provide the ground truths, as they're called, for the network to be able to learn. And now here's the problem, because there's really no good way that you can manually annotate optical flow, because essentially for each pixel you would have to, by eye, judge where that moved from one frame to the next. Even if you were able to do that for one frame, to do it for a few hundred or even a few thousand images, it's just not doable. So the thing that you can do instead is to create your own synthetic data that allows you domain-specific and task-specific training. So we basically make our own data where we take bits of actual images and we move them in a way that where we know how they moved, and use that as training data, because then we have the input data and we know how it moved, so we know what the correct solution of the network should be, and we can train with that. And so the main point there is that the algorithm will end up ignoring occlusions such as tools, shadows, reflections, glare, etc. And we want to also be able to predict retinal motion underneath these occlusions from context. So if there is a surgical target somewhere on the retina and then a tool moves over it and a shadow comes over it and some glare is visible, it should be still tracking that point as best as it can from the context of the retina. So essentially it looks at the rest of the retina and determines, okay, it's currently rotating and moving to the left, so the point will also be rotating and moving to the left. So it basically should fill in the missing information, because it's currently occluded by something from context. And then in the end, we validated this on real video clips, because obviously while you can train on synthetic data, you're actually interested in how that works on real world data. So the overview of the whole thing is this. So we've got our intraoperative data set. It's called RIDE. You can see that in the middle. So on the left-hand side, there's the synthetic data algorithm. So I basically make my own images. I take relatively clear retinal images from what are called the walkthrough videos that just kind of show the retina a little bit before the actual operation starts. And I build my own images from that. I also construct the optical flow ground truth from that. So this is this colorful little picture that you can see there. That's essentially encoding the motion vectors, where the saturation is the magnitude of motion and the hue, or color, is the direction of the motion. So it's it is one way of kind of visualizing a motion field that isn't reliant on drawing in a lot of little vectors. It's not very straightforward to interpret it, but at least you can see, for example, whether there's a smooth transition between different motions in different areas of the image. And so, yeah, the output of that synthetic data algorithm is a pair of images where stuff has moved in between, a pair of segmentations, which mostly show which part is actually retina, which part isn't retina, which we believe should help the neural network to also determine the motion of the retina, because it'll basically help it to differentiate between that and the non-interesting surrounding areas and the ground truth optical flow. So that is then used to train the neural network, which has its kind of classic encoder-decoder structure. There'll be an image later on showing that in a bit more detail. And then we test on actual surgery videos, so a few benchmark sequences that we selected where a lot of stuff is happening that are somewhat challenging because of some such phenomena as I showed earlier, glare, blur, etc., etc. I'll go through the next few slides a bit more quickly because these are kind of more the nitty-gritty of the synthetic data algorithms. So this is how I construct the actual training images. So you can ask the user in the algorithm, you can input what kind of motions you want to have, for example, translation, rotation, or even things like lens distortion. All of these things are added up to a flow field using an optical flow toolset that we wrote ourselves as well, that we use internally. And so from an original just retinal image, we can apply that flow field, and we can also apply some extra things like, for example, this light cone effect that mimics the effect of a light pipe shining in from the left there. And then in the end, we get one image out. And so that is one frame. But then obviously our data set, our network needs 2 frames to learn a motion from. So we do the same thing again with different translation, rotation, whatever, to get the second frame that is somewhat different. Then again, we use the flow toolbox to calculate the optical flow difference between those 2 frames. So this optical flow field now is the motion that converts frame 1 to frame 2, which is what we really want to get in the end in the network, right? We want to be able to input a pair of frames and get as an output the motion field of how I get from frame 1 to frame 2. And actually, this is done on several layers. So the first layer being usually the retina, and then as a second layer, you can have a field of view. Then obviously you can also have different tools, etc. So each layer can be transformed individually. For each layer, you get your own flow field. And you can get masks from an alpha channel in there. And basically you get your frame 1, frame 2 segmentations and the flow. And you can combine that using those masks. And then you get your training data from that. So you have frame 1, frame 2, segmentation 1, segmentation 2, and the flow field. So these the transforms that are implemented here, they should replicate the phenomena visible in the actual real-world data somewhat. So we'll see a few examples here. For example, shadows cast in the retina. On the right-hand side, you can see some synthetic data. And it's clearly not, you can see that it's not the real data, but it's a good kind of simulation of it. Sometimes the tool shaft border isn't entirely clear. You can see here with like low lighting as well. Glare on tools, there's some kind of metallic glare implemented as well. Blurriness, shape distortion, that kind of gives something of a 3D effect to how the tool looks. Then a partially occluded field of view is simulated as well. Uneven and dim lighting, this kind of light cone from the light pipe. You can also see the glare in the light pipe on the left with the synthetic data there. And then partially visible lens and particles or droplets or something like that as well. It's also all simulated. And also even compression artifacts, because that kind of thing can throw the network off otherwise if that's not implemented. So I said before that we want kind of task-specific adaptations. So in this case here, essentially what the actual, so on the left-hand side, we have synthetic data as a frame that I created with the corresponding segmentation and the ground truth flow. But now actually a lot of the phenomena visible here, so this kind of stuff, the glare, moving spots on a lens, a light cone, a shadow, all of that, we actually want the network to ignore, right? We want it to learn the motion of the underlying retina, ignoring these kind of effects. So what we then actually do is we suppress all of this in the output that we want to get. So the light and also light pipe and instrument motions as well. So we take those out of the ground truths for the segmentation and the optical flow. And by training the network with synthetic data that contains those phenomena, by kind of training it to ignore those for the output, we then get it to a point where it can also ignore that for real world data, or at least that's the goal. In terms of the network itself, that's relatively standard unit shape. It's the FlowNet that was published a while ago. I'm trying to update that currently to a slightly more advanced model. I explored we implemented two different architectures essentially. One of them to do with where the segmentation where the segmentation output happens. So with one of them, we've got kind of a secondary part of the network that provides us with the segmentation output, and with the other one, we basically predict the flow and segmentation together at all times. But the overall shape and architecture of it remains the same. Yeah, and then so to get to some results, right? So we want to be able to evaluate that, we compare that to some baselines. The one way of evaluating it when you don't have any ground truth is to use cycle consistency. So in this case, you can use you can put a grid on a video and then track the vertices of the grid. And to get actual values out of it. So this gives you a good qualitative assessment, basically. You can see what happens to the grid and whether it makes sense in the term that it moves. To get a quantitative assessment, you can loop a video so that it plays forward and then backwards again. And if you were tracking the entire thing perfectly, then the grid should return to the perfect original position again. And obviously, we usually not do that quite. So you can then measure what error you get there, and that becomes your quantitative measurement of the error. And so these are traditional methods of tracking. And obviously the problem there is that the tracking mechanism, the tracking algorithms kind of locks on to a lot of really strong features. So you can see it's quite good at tracking strong features on the retina itself. But obviously when a tool moves through, or when you have things like glare, those are kind of tracked frame to frame as well. So the grid is completely destroyed. And also on the right-hand side, you can see it's all a bit, the flow prediction is all a bit blotchy, right? It looks a bit weird. And then there's this other method as well that is in a way even worse. It is even better at latching on to very specific strong features. So that glare on the tool on the right-hand side, that is a really strong feature and that is tracked exceedingly well from frame to frame. The problem is that glare is actually it's not even an object, so you can't even say that it's tracking the tool correctly. It's just something that we would want it to ignore, right? And so in comparison with our method, we got to the point where the grid overall remains consistent. It kind of makes sense, and you can have tools and shadows, etc., moving through, and points underneath that are actually kind of being tracked on the retina. So underneath the tools are being tracked without any issues. So you can see the flow field on the right-hand side. Again, interpreting it is a little bit difficult, but what you can see is that it looks a lot more kind of coherent and consistent, and the tools themselves are basically not really visible. And here another example as well, where the tool kind of moves through the entire field of view, and you can see there's a lot of like sudden motion and rotation, and also kind of stretching towards the side of the field of view, and that is all dealt with relatively well. Obviously, we also have the results in numeric form. I'm not going to go into any detail here. So the conclusions of this essentially is that, one, we developed an algorithm that can create large synthetic data sets of intraoperative image pairs with a corresponding ground truth optical flow field, where you can pretty much just define what type of transformations you want, and it'll apply that and give you sets of synthetic images that you can then use a network to train with. We have also shown that the optical flow learned from correctly designed domain-specific synthetic data, by which I mean in this case, we were suppressing the motion of tools in the optical flow ground truth. So the optical flow learned with that can be used to robustly track points of interest on the retina itself, even in the presence of all these kind of confounding factors that we talked about before, so occlusion, shadows, glare, etc. We also found, you can see that in the actual numerical data, that the complexity of the synthetic data has a significant influence on what tracking performance we achieve. So when we made the synthetic data simpler, we implemented fewer of these things, for example, didn't have shadows on the tools and all of that, that made tracking significantly worse, which argued the other way around means that there's good justification for making the synthetic data algorithm as complicated as it is, because it does actually increase the performance that we get. And also we found that the neural network does benefit from essentially being a multitask network. So it both predicts a segmentation, what is retina, what isn't retina, and predicting the flow, which supports what we initially thought based on the fact that generally where you have a motion discontinuity, so where if you have several objects in a scene that are moving possibly on top of each other, against each other, where you have an object border, essentially where you go from one object to the other, you usually will also have a motion discontinuity because one object might be moving up and the other one will be moving down or something like that. And so predicting both things at the same time are kind of like mutually beneficent tasks or supportive tasks. And so just as a quick kind of outlook, this is a mock-up of what something could look like in a surgical context. So in this case, this is combined with another algorithm that essentially kind of is essentially augmented reality. So it makes the retina transparent, so to say. And then if you register another data modality behind it, so there's ways of seeing the vessels that are deeper down in the retina. For example, you can add that in, but in order to add that in correctly, obviously you need to track points on the retina correctly so that you can add it in at the right point, that it gets moved around the right way, as you can see here. And then, for example, the surgeon could switch between seeing the retina on ground level and seeing kind of into the retina. And you can also there that could be whatever surgical point of interest. For example, you want to inject something there, and that is kind of being tracked robustly despite tools moving around. And this is just a mock-up at this stage, but it's kind of just to give an idea of how this could look in a practical application. In the end, obviously, probably a bit more polished at the end. And yeah, that's pretty much it from me. Thank you.
Thank you, Claudio. Thank you very much. Tiana, I suppose you are moderating questions?
Yes, I think we'll take all of the questions at the end, though. So if you have any questions, please write them in the chat.
Great. So then let me introduce Carlo then. Thank you very much, Claudio, for presenting this aspect of the lab's research. And now Carlo has received his PhD from Imperial College London, from the Hamlin Center. And then he joined our team when we were at UCL. As a postdoc, and he luckily moved with us when we moved to King, where he now has a permanent post establishing the new facilities on manufacturing of instrumentation and clean room facilities and everything. And in parallel, he's doing a lot of work to make our robots first in human trials ready. So he will explain some of the dual concept of what Claudio has been doing, which is the mechatronics aspects of the research in the team. So Carlo, are you here? Yeah, here.
Yes,
I can't
here.
see you.
I'm not sure if my camera is working because it got
No,
frozen.
that's why I couldn't spot you.
A couple of times.
All right.
I'll try to reset it one last time. It probably won't last very long. And anyway, given that we are 5 minutes behind schedule, and usually I'm slow with presentations, I'll just and so can you all see my screen?
Yep.
Okay, thanks for the presentation and also the beautiful previous talk. There will be some concepts that will be recalled in this talk. And so essentially I'll be talking about how we design, essentially optimize, build our robots, and how eventually we also control. A few hints on that. A couple of information on the vision diseases. So there are many pathologies that actually affect the eye, and one of the worst ones is probably the age-related macular degeneration. And in a normal eye with a healthy retina, we can see on the left picture, everything looks nice and uniform. And then we have the macula, which is a dot only a few millimeters in size, basically where we focus 99% of our vision. And so it's sadly with this pathology, the retina starts to die in correspondence of the macular. This pathology can be dry or wet, which involves blood, but essentially the result is that the vision would gradually deteriorate in the center of the field of view, eventually leading to sight loss. So there aren't real, therapies or cures for this that have been already widely adopted, unlike for other issues, like cataract, for instance, which has been fixed for thousands of years now. So in this case, we are at the pioneer end of eye surgery. And so what happens is that the retinal epithelium, so the layer below the retina, so if you look at the top left picture, you can see the retina is basically the top layer, the green one. And so the layer below is actually what feeds the retina. And in these circumstances, this layer is what basically dies, taking with it the retina, which basically is not fed. So there is a pioneering research being carried out also by our collaborator, Professor Lyndon da Cruz. And the idea is basically to replace the lost cells with fresh ones. And this is basically gene therapy. And the idea is basically to inject these cells where they are missing. So essentially in between the retinal layers. So as already mentioned by Claudio, this is extremely challenging because usually the surgeon is holding the tools with his hands or her hands, and there is a natural hand tremor, can be more or less in people, but it will always be there. And when we are working with structures, anatomical structures of such a small size, basically, there are only a few microns in between the layers where the surgeon has to inject the therapy with the needle. And on top of it, if this therapy is injected in the wrong place, it just won't be effective. So finally, the last challenge for the surgeon is essentially that is working with just a qualitative visual feedback, because the surgeon is looking through the microscope, having a view kind of the one on the bottom left. And then the surgeon can switch on the intraoperative OCT, which can give cross-sectional views. But again, it's not a quantitative measure that tells exactly how far the needle tip is from where it needs to be in between the layers. But it's more of a visual information that the surgeon has to adjust continuously in order to search even for the needle tip in the cross-section. And this leads to very long surgeries and that are also extremely technically demanding. So this stops this therapy from being widely adopted, and with robotics we can essentially make it easier so that it can be widely adopted in clinical practice. Other times we have issues with access for instance, in the optic nerve sheath fenestration, sometimes there is too much pressure building up from the brain, and this gets transmitted through the optic nerve to the eye, leading to a reduction in the vision. So the current practice is basically to cut all the muscles around the eye on one side in order to be able to pull the eye out from the socket and essentially reach the optic nerve to perform a small cut to release the pressure. And so once again, robotics can come in handy to solve these problems, access issues, so that the surgery can be done in a more less invasive way. There are many types of robots out there. Probably the most famous ones are the teleoperated systems, where basically the surgeon is holding, let's say, a glorified joystick, more or less, what in the old times we used to call as a master robot. And then there is an actual robot that performs the surgery, repeating exactly what surgeons do. So this is probably the most common type of robot. In recent years, relatively recent years, handheld robotics also became very popular. And in this case, we essentially don't have a big robot with a frame, a standalone frame that is fixed somewhere, but we rather have a compact mobile robot that is held directly by the surgeon in their hands. And if you want, there is kind of a combination of these two, which is the cooperative control systems, because to be honest, this could either be fixed or not, but the main idea is that they are big, they can be fixed, but also they allow the surgeon to collaborate with the robot. And finally, micro robotic systems, which I won't cover in this talk. So we are working at mostly two approaches. One is the cooperative robot you can see on the left. So this robot is basically designed to use off-the-shelf disposable optical tools, like the one you saw in the previous talk, and you can see it's in the center of the left picture. And basically this robot will deploy two instruments, and these two instruments basically would replace what the surgeon normally uses with their hands. And then the surgeon can basically use the handle of the robot to collaborate. On the right hand, we have the picture of another robotic approach that we are working on. And this is a master and slave system. And it's basically a surgical robot that is mounted on a 7 degrees of freedom robotic arm for global positioning. And then once the robot is deployed in the right spot, basically just the robot tip would be actuated. So when working on new robots, we basically have to design and model the system in order to also be able to create a safe control. And this is an advantage that we have compared to systems where robots are not involved, because thanks to robots, we can collect more information and we can basically provide it to the surgeon in a more of an intuitive way, like what Claudio was presenting that is recalled in the bottom right. And at the same time, by having a good knowledge of the robot, we can also support the surgeon better. One of the challenges we have is basically to place the robot in an operating theater as well, and that's why we use visual tools and simulations like 3D CAD models and so on, in order to be able to reconstruct the surgical environment, the OR, and basically make sure that the robot can fit next to the surgeon, that while operating, it wouldn't get in the way of the surgeon or it wouldn't hurt the surgeon or the patient. And we need to accommodate for variations in the patient's anatomy, because the eyes are at different positions, size, and so on. And by doing basically this, all these simulations and data estimation in advance, early stage in the design, we can essentially focus on what are then the real challenges and problems to solve, without basically expecting big surprises in the end, and maybe designing a robot that doesn't even fit in an operating theater. In a similar way, so for instance, for this robot, full modeling of each translations, rotations, transmissions, and joints was performed by modeling the friction, but also the elasticity in the system, in order to have some simulations that are as close as possible to the reality. This can ultimately basically converge towards a full virtual environment where it's possible to even train surgeons using VR, or we could test robot variations or tools and so on. In this case, you can see the engineer is driving more or less like in the real case what the robot would be with its off-the-shelf instruments. And so now, talking about instruments, we can then look at the other typology of robots, which are the flexible ones. So the idea is that a straight rigid instrument basically has to be actuated around its fulcrum point. We saw it in the videos earlier showed by Claudio, and you can also see it in the in the top right picture. So the insertion point of the tool is where the tool will be able to basically swing about. And that can cause local lesions that could lead to a loss of pressure within the eye, or rather it could even cause intraocular lens damage or retinal damage. So the idea is actually to replace these fixed tools that need to move from the outside, essentially. Sorry, I said fixed, I meant rigid. With flexible tools that are fixed on the outside and where basically the whole motion happens within the eye, already on the inside at the tip. And the tool tips can be basically what surgeons are currently used to already. So to do this, we are using super elastic tubes that are made of nitinol. And the idea is that these tubes are concentric, meaning they fit one into the other. And they are also telescopic. They can translate with respect to the other. So by translating and rotating them in different configurations, we can essentially obtain a final tip position with a specific orientation. Here is an example of one of our robots, basically following a helix trajectory. And this was being tracked to compare it basically to the desired trajectory. There are small instances in which, as you can see in the green trajectory, is not as close to the desired one, and that's usually because concentric tube robots depend on the torsion and elasticity of the system, and therefore there are times where there are slight jumps and so on. So a good control would also minimize this. So this second robot we're working on essentially features one robotic end effector, let's say, that is mounted on the supporting arm. And this end effector has basically a tool that is quickly replaceable. These tools feature 3 tubes, each with 2 degrees of freedom for a total of 6. And they feature a quick plug-in interface that uses magnets. And the ability of using flexible tools means that we can also explore different access routes. Recent work that was presented at IROS was proposing basically an orbital approach to the optic nerve fenestration. And you can see the video of the robotic system that was used for this experiment. In this case, the tools, so the robot is a multi-tool one. It has 3 instruments, 2 are surgical instruments and 1 is for the camera. And the instruments have 4 degrees of freedom each, so 2 tubes each. So we had to study the access route and optimize the workspace volume to be sure we had enough to play with at the back of the eye. And yes, basically the video. So the picture on the left shows the reachable basically points at the back of the eye, while the videos on the right show different phases of the insertion. In order to be able to know whether the robot can actually perform the task, we also had to measure the forces required to penetrate the optic nerve in a porcine model, so that we were able to measure the insertion forces, but also the stiffness of the eye, and be able to also create, a high fidelity looking phantom. And during the experiment, in the end, the whole procedure was tested by grasping, as you can see the tool on the right, grasping the optic nerve, and then basically using the left needle tool to actually insert it into the optic nerve. And maybe I'll say a few words on controlling these robots. So after design and modeling these robots, the last and closely to most important item is a safe control. And with concentric tube robots, it's quite it's quite a big problem actually to have a safe control, because there is not an easy way to actually obtain inverse kinematics. And because it's not like common serial robots where, let's say, either you pull a tendon or you rotate a joint and so on, and the robot moves in that direction. Here it all depends on elasticity, torsion, diameters, curvature ratios, and whatsoever. So the issue is that it's highly unpredictable and counterintuitive. So it's also computationally expensive. So the issue is that we could pre-plan all the access routes and so on, but then we wouldn't be able to account for changes in of the anatomy, for example, within the day. Maybe the target you want to reach is a little bit more swollen today than yesterday when the scan and the pre-planning was performed and so on. So it's essentially better to have an online kinematic algorithm, inverse kinematic, that allows you to reach stable configurations at the tip, and also at the joint space, and that allows you to avoid collisions where you don't want, or that allows you to stay within on top of your target and things like that, all by basically understanding and executing what the surgeon wants to do. Also potentially providing haptic feedback and so on. So this is the good role of a good kinematics. Sorry, is the objectives of a good kinematic model. So there are several models out there, algorithms used to solve these problems, but none of them is actually perfect. So our center decided to explore the possibility of actually running them all in parallel and then choosing the best results, essentially. I'm not going to go into the details, but 7 different algorithms were run in parallel with local and global optimization for a total of 25 different combinations that is possible to choose from. And as you can see in the pictures, in the left, you can see the standard model from the literature, while on the right hand, you can see the one developed at our center. And as you can see, the desired trajectory is followed more closely in the right hand video than in the model on the left, where you can see the desired trajectory is the green one, is quite far at times from the blue one. So the tip position is followed correctly, but the orientation is not in most of the cases. So with our model, we can then essentially create, again, virtual models that can replicate exactly or very closely what happens in reality. And we could use these tools also to train surgeons without the need of necessarily deploying the real system, because we have a good degree of control and knowledge of the system. Finally, one last thing that can be added is the possibility of also implementing active constraints, which basically it's a bit like the guidance provided by, let's say, your parents when we were all small and we were going for the one too many sweets, and the parents would basically stop your hand from grabbing one. So this is kind of what that does. It's possible to define virtual springs, and these springs can essentially stop you from reaching certain areas that are off limits, or they could help you stay focused, for instance, on an insertion path that you want to follow, or rather on a surgical target that you want to manipulate. So just to conclude, we are working at different robotics systems. We have co-manipulated robots where the integration in the clinical work is a little bit easier, because the robot uses off-the-shelf tools, and it's designed to be added essentially to the current surgical workflow. And there is direct clinical supervision because the surgeon is touching the robot directly. And it does enhance dexterity, and it removes tremor, so these are great advantages. It increases precision because we can know exactly now where the tooltip is. But at the same time, it's still using a remote center of motion. So our single or multi-arm flexible robots are basically have an increased dexterity because they have pretty much micro-sized wrists. And at the same time, they increase the capacity for challenging interventions because we can reach areas that were not possible before, or because we can be more delicate, more precise in injecting something. And on the other hand, they are highly counterintuitive to control. So thank you all for your time, and happy to answer questions. Want to thank the whole team. Actually, the people from UCL are missing, but thank you also to all our partners.
Super, Carlo.
Thank you both so much for your talks. They were very, very interesting. I'm sure everyone listening will agree. We'll go to questions now. I think Vanessa is going to take over that. Again, if you have any questions you'd like to ask, raise your hand, or I know some people don't like talking in the chat, talking on the call, drop them in the chat if you want.
Yeah, so the first question for Claudio, can you explain again the benefits of using cycle consistency in your work?
Right. So yeah. So this is to do with the problem of evaluating this, right? So the same reason why we're using synthetic data to begin with to train the network is also why we need to use this to evaluate it, which is we don't really have much in the way of ground truths that you can compare anything with, right? So if you don't have if you don't know the true motion, you can either train the network with that, which is why we need the synthetic data, but you can also then not really easily evaluate any output, because what will you evaluate it against, right? And so the idea of looping a video kind of forward and backwards means that you can essentially compare it against itself, right? Because the ideal tracking will go from the beginning, the start of the video situation, to the end, and then back to the start, and it should, in theory, perfectly match, which it'll never perfectly do in any realistic system, but then you can calculate by how much it doesn't match, right? So that's essentially a roundabout way of getting some kind of quantitative evaluation where you don't really otherwise have anything.
Right, fantastic, thank you very much. And I think this question was for Carlo. How do the robots quantify force on the optic nerve?
Sorry, I'm sorry, I didn't hear.
Sorry, how do the robots quantify the force on the optic nerve?
That's actually a very good question. So in the experiment that was performed, it wasn't the actual surgical robot performing the measure, but it was a separate linear actuator, a linear robot essentially with a force sensor that was performing the task. And that was basically to measure the forces that we require in order to be able to test on the side whether we can achieve that with our own robot. But you touched a very important point, because force feedback is a big goal to achieve, actually. And basically most of the surgical platform out there either don't have it or is under development, because it's actually quite challenging to do it. There are several ways. It could be that it's possible to use either disposable sensors, but that's a route that is not explored too much yet, it seems. Otherwise, it's possible to use modeling, and modeling is a good way to get an estimate of the forces. Other possibilities could be to have force sensors placed within the actuation unit of the robot. On the other hand, by doing so, you also have a lot of other inputs and effects that will affect your measures from in the transmission chain that goes from the motors to the tooltips. So probably the right approach will involve a bit of everything with a bit of AI learning as well to remove these, for instance, friction influences or torsional effects within the elastic tubes and so on.
Great, thank you. We have another question. What do you think are the next steps for your research and its applications? I think that's for both.
Is this for both of us, or?
Yeah, I think it might. Yeah.
Next steps on the hardware. On the hardware side of things, well, improving manufacturing tolerances and practices. Also looking forward to moving into a quality management system in order to then one day reach the first in human and so on. So that would be a big goal. Miniaturization is usually also another big task to perform. It's always useful. And yeah, I think on the hardware side is mostly these things, and force feedback would be a good one, a good goal.
Yeah, I think on my side, the ultimate goal obviously would be to deploy this in an actual operating theater, either to increase the amount of information that is available to surgeons now, or to help with the use of robotic tools such as the ones that Carlo was talking about. Yeah, I mean, surgeons will still be operating those, right? But you can, with the right computer vision tools, you can help with a lot of stuff. As an example, you could make the tool lock on to a certain point on the retina and automatically move with it, so that the surgeon has to worry less about making up for some of the movements, just as an example. And in the more short term, I'm working on improving the actual deep learning kind of network side of things, different network architectures, and I think possibly leveraging the fact that we have a very large, though unlabeled data set, maybe with by using self-supervision, but that's a whole new thing that I kind of am trying to get into. So.
And how long does this process from design and research to deployment normally take, would you say?
I mean, from my side, it's quite hard to gauge. I mean, generally we're talking about years and years, right? So this is more in the order of at least half decades, rather than doing something in a few months and then it's out there. In terms, I think, of the overall thing, anything deployed in an actual medical context will have to go through a lot of certification, etc. So that makes it's not the type of thing where you're a little startup, you come in and you disrupt the industry, and then a few months down the line you have something that does something. That's just not really how you do things in a medical context, right? So even if the actual development is really fast, getting to a point where this will actually be used in an operating theater, even if you have the surgeons actually interested in using it, and you've been able to convince people that this will provide a big benefit, etc. So even if all of that is not an issue at all, just going through the official steps takes years and years. So it's unfortunately something where progress is a bit slow.
And that leads on quite nicely to the next question. So are surgeons showing interest in the robot, or are they reluctant to using this new technology, would you say?
Well, I would say that, I mean, not specifically to this robot. I will say something in general now, and then go a little bit more specific. I mean, our surgical team is extremely excited to work with us to contribute to ideating, designing, and then testing the robot. So definitely we have great feedback. I can say in more general, surgeons they like robots. The only thing that mostly they are worried about is to lose control and not being in charge. So this is where that smooth integration and, let's say, collaboration where it's needed between the robot and the surgeon is required in order to, make the surgeon feel comfortable in using the robot, and possibly even sometimes giving up some degree of control. But at the same time carrying out very safe surgical operations. And there are already out there robots that are surgical and that they are partially or fully autonomous. I think one example is in orthopedic surgery where they do the knee replacement. They can basically pre-plan all the robot trajectories, have the legs fixed where they need to be, and then the robot does all the drilling precisely and so on.
I think Tiana has her hand up.
Yeah, I do. I didn't know what the protocol was for me asking questions. So I was just wondering, obviously these robots aren't all the same size, they don't all have the same specifications, but I guess leading on from that question you just answered, how practical do you think it is that these will be implemented in hospitals or in surgeries? Because do they have the space for them?
Yeah, that's again, it's another very good question. Usually the OR is crammed and jammed with all sort of trolleys, cables, things on the floor, pedals, and so on. So definitely keeping the smallest footprint possible is a big objective. And yeah, this is also where certain robots become, more interesting. Like if you have a compact robot rather than a bigger one, or if you have a handheld solution instead of a fixed frame robot, and these kind of things. What I can say is that for sure they would find space if they find it useful. Because in the same way as in an operating theater, you will always find the surgical bed, the surgical lights, the trolleys with all the tools and so on. It basically depends on what will be the surgical, the operating theater of the future. Basically, we will replace certain tools for other ones. But ultimately, if it's useful, the place is there. And while engineers have to aim to build smaller things rather than bigger ones.
Okay. I said thank you, I was muted.
Oh, cheers.
Yeah, I think we have one more question from Sally. So are there any fail-safes?
Yes and no, in the sense of that the robots, well, most of the robots we are working on are at the, I mean, they are not at the translational stage yet. So essentially, we are not required to have fail-safes. At the same time, I can tell you, we on one of the robots we are working, we have redundant encoders so that we can measure the rotation of the motors, but also the actual position of the tools. Apologies. And in other cases, one thing we will add soon is limit switches and so on. So for when it comes that the robot would eventually be deployed in a first in human and so on, there is where you actually need all these safety precautions and fail safes and so on. But that's for requirement for regulatory approval. So there would be, emergency switches, protocols on how to switch off the system in a safe way, or rather, if the communication goes wrong, what does the robot do, and so on. It becomes very, very fine. The safety aspect of a robot, and it will definitely require a high degree of redundancy. I saw another hand, Tiana. Is it for me, the question?
Yeah, well, it's kind of for both of you, but I think it might be more for you. So you just mentioned protocols and regulations. I was just wondering, have you put any of these devices forward to any like regulatory bodies? Have you had any response from them? Like, what are the protocols for this? Do they have any?
So not yet in this case, but it's definitely a step that we will go forward. And I actually, during my PhD at Imperial, I was part of the team that applied for MHRA with a robot that I designed with another guy as well. And so, yeah, I did see the process. It's almost, I don't know, like it's more like of a low field almost than engineering. But at the end of the day, the point is you need good practices in the design and keeping the design history in order to be able to basically justify all the design choices done. Of course, you need to have traceability of the materials and the manufacturing processes should be, again, should be formalized into proper protocols that can be followed and that can be replicated, because that's basically the whole point. You don't want to build the one-off research robot prototype, but at that stage, you want to be able to build consistently tools that all have the same properties, that are all made in the same way, and so on. And then the surgical classification also varies a lot, the amount of information you need to provide. It's very different if the surgical class of a device is class 1, 2 or 3. Basically, the higher the class, the more the paperwork essentially, and the more constraints you have to respect.
Okay, thank you.
Cheers.
If anyone else has any questions, feel free to unmute your mics and ask now or pop them in the chat. If not, I'll hand back over to Tiana.
Yeah, any other questions? I guess the loud silence is a no. Okay, so to wrap up, I want to say a big thank you to Carlo and Claudio and Christos. Clearly, you're very busy by the fact that Christos had to run off. We really do appreciate it. Out of all the requests we have for talks, it's either robotics or AI. And so we're really, really happy to have you. And normally if we were in a lecture room, we'd all applaud, but I think it'll be a little bit awkward on Teams. So it's just a big thank you.
Thank you for the possibility to present here. It was great fun and lovely audience with the interesting questions. So yeah, great. Invite us back again.
We may do next year because we'll have even more requests. Right. If you guys missed anything that they said, because I know some of it was a little bit complicated, some of the diagrams, we have recorded this and we started a YouTube channel. So we'll be posting it there I know we have 0 subscribers at the moment, so if you feel like subscribing,
So what you're saying is please like and subscribe.
yeah, like, subscribe,
Yeah.
drop a comment. Yeah, so if you missed anything, we'll be posting links to that if you want to check it out or send it to someone. Yeah. So thank you.
Just very quickly, before you finish, Chris has asked me to mention that there is currently a PhD position, I think, open, as in he's looking for candidates in the area of kind of computer vision, tracking, etc. So if anyone is interested / knows someone, then that might be something to look into. Generally, I think our lab, often has positions open, so it can never hurt to ask, essentially. Also the same for projects, BNG projects or summer projects or whatever. So
If people wanted more information on that, where could they find it, or should they just email Christos?
I think the easiest thing would be to email. We do have a website, but it is being built up, I believe. I think it's arvin.online, if I remember correctly.
Yeah, it's
yeah,
correct.
I will put that in the chat. Yeah, that gives a little bit of information about the kind of different publications and people and projects and all of that. It's maybe not complete yet, but it's kind of slowly being built up. So at least it gives some idea.
Thank you. That sounds like a great opportunity. I'm sure people here will be interested to look at it.
Thanks.
So yeah, thank you again. I hope you guys all enjoyed it. I did. And have a good evening.
You too. All right.
You too.
Bye-bye.
Thank you.
Thank you all. Bye bye.
Thank you.
Thank you, everyone.